Alright, now we're going to solve a system of linear equations using the row operations that we learned last time. And I wrote those row operations down here for reference. And remember, the first step is to put all of the coefficients and the solutions into a matrix. So we're going to do that, starting with the coefficients. So we have the first equation, negative 3, x minus y plus 3z, and that equals negative 3. We don't have an x in the second equation, but we have a negative 2y and a negative 1z, and that's equal to 1. And in our third equation we have 3x, 2y, and negative 3z, that's equal to 0. And that is our augmented matrix. And now what our goal is, we need to get this augmented matrix into what we call row echelon form. And all that means is we need to get ones across the diagonal and zeros below the diagonal. And that's specifically for this type of matrix. I'll go over a few different types at the end, but this way is the easiest to learn. Alright, so we want ones here and zeros here. So how do we do that? Well, I can see right off the bat that if we add the first row and the third row, we can get rid of one of these 3's and get a 0. So that's what I'm going to start off with. I'm going to say we're going to add row 1 and 3. And since I don't like dealing with negative numbers, I'm going to replace row 1 with our new row. So we have 3 plus negative 3 is 0, 2 plus negative 1 is 1, negative 3 plus 3 is another 0, and 0 plus negative 3 is another negative 3. Now all the rest stays the same. And now, since I don't want a 0 up here, I'm going to move this whole row down to the third one. So I'm going to swap rows 1 and row 3. I'm going to swap rows 1 and 3. Alright, we're one step closer. Now I want to get a 0 here. And again, I don't like dealing with negative numbers, so I'm actually going to get a 0 here and then swap those two rows. So what I'm going to do now is 2. I'm going to go down here, 2 times row 3. So that's scaling, right? And then we're going to add at the same time, plus row 2. So we're actually doing 2 of the row operations this time. 0 plus negative 1 is negative 1, and then 2 times negative 3 is negative 6, plus 1 is negative 5. And then we keep our third row the same. And now, like I said, I'm going to swap those two rows. And now we have our 3 zeros in the bottom. Alright, now row 3 is going to be super easy to get this into a 1. Right now it's at a negative 1. But all we have to do is scale that whole row by a negative 1 to give us a 1 here. So instead of writing a whole new matrix just for that, I'm just going to write down here below our arrow negative row 3. And then I'm going to erase our negative signs here real quick. And now we can focus on making this a 1. So all we're going to do is divide row 1 by 3, and that should give us a 1 right here. So I'm going to do 1/3 times row 1 That'll give us a 1 here, 2/3, -1, and 0. Okay, and now we are in row echelon form. We have two options from here. We can rewrite our system of linear equations using these new coefficients and these new solutions. So I'll do that real quick. We have 1x plus 2/3 y minus z equals 0. We have no x's, but we do have a y, no z's, and that equals -3. And we have z equals 5. So now we have y and z already, so we can just plug those in up here and figure out what x is pretty easily. And that's one way of solving this. But the other way is to continue with our matrix and put this in reduced row echelon form. So we're going past row echelon form into reduced row echelon form. And all that means is now we need to make these zeros as well. And we can do that by multiplying row 2 by -2/3 and adding it to row 1. And that should cancel out this 2/3. So I'm going to do that. -2/3 times row 1. And it will give us 1, 0, -1, and -2/3 times -3 is 2, plus 0 is 2. Then the rest remains the same. And now we just need to make this a 0 by adding rows 3 and 1. Five plus 2 is 7. And the rest is unchanged. Okay, so now we know that if we rewrite this system of equations, we have 1x equals 7, y equals -3, and z equals 5. And those are both ways of solving this type of system of linear equations. But I did say earlier that I would show you some different matrices that are a little bit different. So what if you didn't have a square matrix, but instead you had a 4x2 matrix? So you have this type of matrix. Now what you can do here is you can tell that the diagonal doesn't reach all the way down to the bottom, right? So how does this work? Well, the form for a row echelon form would be 1, 1, and this doesn't matter what this value is up here, but the rest underneath of those would have to be zeros. Reduced row echelon form would make this a 0 as well. And what about the opposite way? What if we have a 2x4 matrix? Now this is a bit different because we don't just have one option. Alright, so we could say 1 here, then a 0, then a 1. But it doesn't have to be that way. Okay, so this leading entry here, leading entry being the first non-zero term in a row, that leading entry doesn't have to be in the column directly to the right of this leading entry, or the previous leading entry, okay? So it could be like this. Or it could be like this. Okay, now I will show you what reduced row echelon form would look like. So in this case, reduced row echelon form, you're looking at the leading entry specifically. So above all of the leading entries, you'll need to have a 0. So our leading entry here has to have a 0 above it. Our leading entry over here has to have a 0 above it. And our leading entry over here has to have a 0 above it. But what does this mean for the solution? For the columns with leading entries, those are going to be the bound variables. Okay, so if we were doing x, y, z, a, let's just say, in our first situation, the bound variables would be x and y. In this second situation, there would be x and z, and in the last situation, it would be x and a. The other two variables are called free variables, and they can be whatever we want. Normally we would plug in parametric variables for them, s and t, but we'll deal more with that when we get into the null space. I should let you know that all of these types of matrices work the same as the first example we did. You can scale the rows, you can swap the rows, you can add two rows together. That hasn't changed at all, and these examples that I have written down aren't augmented matrices. It still works without augmented matrices. It works both with and without augmented matrices, so you don't have to worry about that. And I hope that helps. Good luck on your test tomorrow. See you in the next one.